Hi, everyone. Welcome to Foresight Space Group. I'm super excited to not only be here today with Creon Levitt, but also Lindy Elkins-Tanton. Thank you so much for joining us. Creon, please take it away with your intro to Lindy, and I will be in the chat. I'll share a lot more info about you, Lindy, in the chat with people, and we'll hopefully hear a lot more in a second.
Okay, great. Well, my intro to Lindy, I'm going to speak personally because you can look at her bio and things in the links. We have worked together on a project for a long time. I at least haven't been so involved in the last couple of years. But it's a really cool project. We'll talk about it later. And I was so out of the loop on this stuff that I didn't even know until preparing for this meeting that Lindy was the PI for the Psyche mission and the proposer for the Psyche mission, as I understand it. So did a little homework. And so obviously that's not all we're going to talk about, but this is the topic du jour. And Lindy, if you want to say anything about your history or our history, fine. Or if you want to just dive right in and tell us the basics of Psyche, the asteroid, what was known, and then the mission and how it came to be and where it's at, that would be great.
Yeah, I might start with a cut. First of all, thank you very much for inviting me. It's really fun to be here and great to be talking to you again, Creon. It's been a while. I want to just set the stage for a couple things about my own work in case it becomes of interest. In addition to Psyche mission, which I will talk about in a second, also founded at Arizona State University, the Interplanetary Initiative. And I see Jessica Rousset, who's our director, is on. Hi, Jessica. This is a pan-university initiative at ASU to bring together all disciplines to think about space futures. And so we do things that are relatively similar to Foresight in certain ways. Over the last 8 years, we've been developing new ways to bring together interdisciplinary research teams, and we've seed-funded 45 research projects. And we work cross-sector outside of the university as well as interdisciplinarily inside the university. We have our own future-facing undergraduate degree with 115 majors. And we work with a lot of space groups around the world, I think, trying to do fairly similar and aligned things. And that includes Open Lunar, which is the project that Creon and I have worked on together. So that's a kind of a broader picture. Psyche mission. This started, so first of all, Psyche mission is named after the asteroid 16 Psyche. Every asteroid, as I'm sure that you all know, has a number based on the numerical order in which it was discovered. So Psyche was the 16th one, discovered in 1852 out of the observatory in Naples, Italy, and named Psyche after the goddess by its discoverer. And when we started our proposal process, which Creon alluded to, we were faced with an interesting marketing issue, which was most of the reviewers reading this proposal had never heard of this asteroid. And so I decided to avoid the NASA acronym trap. And we just named the mission Psyche after the place that we're going in the hopes that it could help people remember what it was about. So from the Earth, our remote sensing...
Wait a minute. So
yeah.
So did you backronym and what is it?
It's not. It's just the name, Psyche.
Oh, okay. Got it.
Yeah. So we could make up an acronym, a retrospective acronym.
Or a backronym, as they call it.
Yeah, a backronym. Exactly. Yeah. So we haven't done that yet. We should apparently do that. Yeah. So back in 2011, I'd written a paper with my colleagues, Maria Zuber and Ben Weiss, about these earliest bodies to form in the solar system, planetesimals, these little planets the size of cities or continents that formed in their thousands in the first moments of the solar system, the first couple of million years out of the 4.567 billions of years that our solar system is. So if the solar system was a 24-hour day, they formed in the first 30 seconds. And they became the feeding material to build rocky planets, except for a few of them got stranded in the asteroid belt. And we think that Psyche, this asteroid that we're interested in, might be the metal core of one of these planetesimals that melted and had its metal sink to the middle, because we think it's made of metal. So in this paper, I was talking about formation of cores, and I got an email from a couple guys at Jet Propulsion Laboratory saying, we really like this paper. Why don't you propose a mission to test your ideas? And it took us about 6 months to find the place we could go in our solar system to test our ideas, because we're never getting to our core or the cores of the other rocky planets. But there's about 9 asteroids out of the over 1 million known that seem to be made mostly of metal, have a metal surface, and Psyche's the biggest one. So then we went into a 3-year competition process in NASA's Discovery program starting in 2014. And we competed against 28 other missions. We wrote a 200-page step 1 proposal and a 1,000-page step 2 proposal with 150 people. And in 2017, we were selected for flight. And so we've been building the spacecraft since then, going through a giant roller coaster, out west rodeo of experiences, getting to launch just over a year ago. We launched October 13th, 2023, and we will get to the asteroid in 2029. So that's my little Psyche story. And the update on the mission is it is going great. We are, today is mission day 379, and all is nominal in space speak.
So could you perhaps say, I'm just going to do this at random and then we'll collect questions in the chat or for live audio later on or while we're talking. There are different classes of NASA missions and they have different calls for proposals. And can you say a little something about the particulars of the class of mission that you responded to and how it affected the design of the mission?
Yeah, great question. The biggest NASA missions are flagship missions like the Mars rovers or Europa Clipper that just launched using the same side boosters that were on our rocket, by the way. And yes, that was awesome. So these flagship missions are designed and led out of headquarters, but the other missions are competed. And so there's New Frontiers, which is the largest competed class by budget, and then Discovery is second largest, and then there are a whole bunch of other programs. And when you compete for a mission, the mission is generally led by a scientist, and that scientist puts together a team of a NASA center that can manage the mission and an industry partner that can build some part of the spacecraft, like the spacecraft bus, for example, or the power system. And then working together with those partners, put together a giant team of engineers and artists and budgeters and schedulers and writers and scientists, all the people that you need to run the mission. And in our case, Discovery, we were given a cost cap of just phases A through D. So not actually the cruise and science part of the mission. And we had to design a mission that would fit into that cost cap. And we did that a couple of different ways. It's very hard to go into deep space under these cost caps. It's amazing how expensive NASA missions are. And we are all aware of this. And it kept blowing my mind. Like, I'm used to commercial business where you could say, let's figure out how we can drive this cost down. And a lot of times the answer would be, can't. And so one of the ways that we got in the cost cap was by choosing Maxar as our prime contractor. And this was Maxar's first time to ever be NASA prime, and they really wanted it. And their advantage was they fly solar electric propulsion missions. And we knew that the only way to get out to this asteroid, which is often closer to Jupiter than it is to Earth, it's in the outer main belt, was with solar electric under this cost cap. And they had these off the shelf, basically like production line models of solar electric spacecraft that they used for commercial Earth orbiting communication satellites. So we picked their smallest off the line model and just did a few alterations, and they gave us a firm fixed price. And so then there's a NASA cost model where you plug in everything you want to build and it gives you the NASA estimate. And we broke the NASA estimate, I can't remember now, well over $100 million with the firm fixed price, which worked out great. So
you mean that you came in $100 million under the cap?
Not under the cap. We were under the cap, but under the NASA prediction of what it would be. Yeah. Yeah. So firm fixed price. So that's a little example of what you have to do to fit into these competed missions.
Okay. So let's talk now, if you don't mind, about the science payloads, the instruments, and what was chosen, what was dropped, and why, and what it means. What's it going to tell us?
Yeah. Oh my gosh. That so much of this journey has been a mind-blowing journey of team leadership. And I will just preface this by saying, thank God I worked as a management consultant before I went back for my Ph.D. It really helped. And in fact, I'm now writing a book about how teams work best based on these insane experiences and others. So I was under a lot of pressure right away, right out of the gate, to pick my science team. I was supposed to pick the science team, the most famous, sought-after scientists in the world, so that other proposing teams couldn't have them. It was a first strike strategic move, but I was not willing to pick any scientist who came with a favorite instrument or a science instrument that they built, because that would constrain the design of the spacecraft right from the beginning. So we wanted to actually work our science traceability matrix from left to like you're supposed to, like the big question, the answerable questions, the measurements we need to make, the instruments needed for those measurements, before we picked the people with the instruments. And so we did a pretty good job of that. We picked imagers built by Malin Space Science Systems, led by Jim Bell out of Arizona State. This was before I moved to Arizona State, so it was a funny coincidence. And we picked magnetometers because we hope this body has a big magnetic field out of UCLA. We ended up having to change the vendor right before CDR. That was exciting. And we picked a gamma ray and neutron spectrometer. Originally, we picked the Russian one, which I'm now glad that we had to change our mind because NASA put in a policy about the percentage cost of science instruments that could be provided by a non-US vendor. Because the problem is NASA has no leverage if somebody's not delivering from overseas. And so that's been a problem in the past. If they're delivering from home and they're slow, we can push them. So those are our three big science instruments: gamma ray, neutron spectrometer for composition, magnetometers for magnetic field, imagers to get pictures and topography. And then we'll run a gravity experiment using the radio, so Doppler gravity. We thought we were going to have room for a laser altimeter. And I really wanted a laser altimeter. And we brought Maria Zuber on board with her laser altimeter. And then we discovered that we could not fit it into the cost cap. And so that was the one super awkward conversation, was to have breakfast with Maria, who's been a great mentor and friend of mine, and in fact was the chair of my Ph.D. thesis committee, and tell her that we're not going to fly her instrument. But she was very good-natured and understanding and got the kind of constraints we were in, understood why, and stayed on the team. So that turned out well. But oh my gosh, the complexity of these decision makings, and to go to a body where we're not really sure what it's made of and try to choose instruments that'll let us determine that, no matter where on the spectrum of possible psyches it is.
Cool. But now, if I'm not mistaken, or perhaps this is old information, there is an interesting laser technology on board this spacecraft, is there not?
Yes. Yeah. So we're flying a NASA technology demonstration. With many of these missions, NASA offers you several different things that they want to get flight heritage on and practice in space, instruments to fly with your spacecraft. And they give you a token amount of money, which seems useful at the time. And later, it turns out it costs so much more to integrate a new instrument than the bit of money. So it was a really interesting challenge all the way along. But we got to fly this instrument. I'm so excited about it. The Deep Space Optical Communications package. So this is practicing streaming data from deep space using a laser that can have a lot more data encoded in it than radio. So for our prime mission, it's all radio, but we're doing this tech demo. And so the tech demo has been on for the greater part of the first year of flight, and then it'll be on some more next year, and then it'll be done. But it has succeeded beyond, I would say, my wildest dreams. It's been incredibly successful. It did a special thing, which was we had uploaded an art video onto the spacecraft, onto the Deep Space Optical Com, and they sent it via laser from 80 times farther than the moon at 267 megabits per second. So this faster than my home internet. They sent it from 80 times further than the moon, and it was an art video about a cat chasing a laser. And this cat's name is Taters. It belongs to one of our team members, and is now an international star. Taters, the space cat.
International, not just international. Yeah, interplanetary star. Yeah.
At least interplanetary.
Is this, just a side tangent here, does this laser comm system relate to the one that was flown on Laddie, if you know about that?
It's the next generation from that one. Yeah.
Okay.
Yeah. And it has, oh my gosh, the technology is amazing. Bill Klipstein is the lead for that project at JPL. And I think he could do anything. I think he could build anything, make anything happen. Like during COVID, he moved to Massachusetts to put pressure on one of the subs who was late and showed up at their place every day. Like, he is unstoppable. They had to build at one California observatory a sending laser with all of those
Oh,
constraints.
this is a bidirectional laser link?
Yep. Yep, exactly. And so that involves discussions with the FAA and all kinds of things. And then they had to build a receiving link at 2 other California observatories, plus the technology on the spacecraft itself. And the receiving link is an array of superconducting nanowires where if they're hit by a single photon from the Psyche spacecraft, they lose their superconductivity and register its arrival. And I will just add one other thing about this technology, which is we have very good pointing accuracy on the spacecraft because we've got to be able to point at the deep space network from very far away, 3 AU distance, more or less, from the Earth. And I should be able to tell you the numbers, but they're not in my head right now. But it wasn't good enough pointing for the laser comm. So they redesigned the instrument so that it detaches completely from the spacecraft, floats free in space in a little cage, and then points itself with electromagnets so that it has even better pointing than the spacecraft. They had to invent that technology and then the lockdown technology to keep it safe when it's not doing that. Amazing.
Yeah. One last question about the laser comm system. It's not so often the case, but it is cloudy in California, and California is not always facing the spacecraft. So what happens? You get these high rates unless you don't, right?
This was, so I was completely new to the idea of laser comms when we went into this because it's just comms is not my field. And I was dismayed to learn that these lasers do not go through clouds. And then when it's cloudy, the whole thing fails. And so when we go all laser comm, we'll just be using these networks of satellites to relay around the Earth to a non-cloudy area. We had opportunities over and over through the mission. We have to stop thrusting and turn in order to use this technology. And with solar electric propulsion, you're thrusting almost all the time. So it's a big disturbance to our ops, and we had it very carefully scheduled. And sometimes it would be cloudy and they couldn't do it. But yeah.
Oh, as for the radio part, what do you use the Deep Space Network?
Yeah. Yep.
Okay. Cool. COVID. And I noticed you had a little thing in your abstract. I'm wondering if we might briefly take a pivot here and talk about some of these broader ideas you have about not so much COVID and how it affected the project, although feel free, but the broader ideas about continuity of culture and knowledge.
Yes. Let me start by saying this is where the seeds of these ideas came. First of all, from Interplanetary Initiative, thinking about how do we set up society to be ready to be interplanetary? How can we do this with our best selves? How do we change education so people are ready? These things that Jessica and I and our team are working on really all the time. And in fact, we're going to be growing this initiative at the university over this coming year to an even much bigger thing. So during Psyche mission, first this happened with one of the vendors who was doing part of our comm system. They just couldn't get it tuned. And these are what are called cost plus contracts, your standard government contract, which if you don't know means that if they can't build it, then you have to pay them to try again. And this did not align with my ethical sense of the world. But it turned out that some of these items are asked for so seldom that they don't really they're not a production line item. It's a big risk for the company, I understand. So they couldn't tune this thing. And it turned out the reason they couldn't tune it is because the person who knew how to tune it had retired. And they had not actually trained anybody else to do it. And so we brought her back in from retirement. Her name was Helen. And she tuned the stuff and it worked. Then another company in another part of the country couldn't make their little piece of our subsystem that they needed to make. And again, people had retired and not passed on the knowledge. And in this case, the person's name was again Helen. So there were 5 or 6 times during the mission where this happened. These are the only 2 named Helen, but it made my son and I start thinking, how do you actually pass on knowledge? How do you stop people from losing the recipe? Like, why could the Romans make better concrete than we can make today? Why do we have to rediscover this? What happened to our knowledge? We started thinking of the Helen as the unit of least technological knowledge. This is one unit of technological knowledge that you need. And then thinking about going forward, I don't know how you all are feeling, but I'm not feeling like the world is in a very good place. And we're really vulnerable to more pandemics and to dictators and to wars. And then also to population decline. So we're near we think, peak of human population, and it's going to start dropping down, which on the one hand is really good for our planet and maybe for humans too. But also we don't get to, so we don't get to decide what knowledge is not replaced. We don't get to decide where our fabric wears holes in it from people disappearing. So I started thinking about the need for through lines, the need for combination human and AR, VR communities that would be the owners of the knowledge that has to be persistent through a human futures to avoid another dark ages, basically, in its kind of saddest state. And I tend to be an optimistic person, and I know that we're going to get through all of this. But the question would be, how do we get through it in the best possible way? And I really believe that it would be good to put together these through lines, and also that human knowledge is best passed in an apprenticeship model, shoulder to shoulder. You don't learn things by reading them, but we could make AR, VR experiences that are almost as good as apprenticeships. And these are things I've been thinking about.
Yeah, all you have to do is watch some YouTube DIY videos, and that becomes pretty apparent. Like I just watched one the other night of this guy setting up this lighting, building this lighting, this weird thing. And oh my God, I now know every single thing. It's as if he came to my house and gave me a private lesson. Okay. By the way, I did a big study many years back at the request of NASA on the lessons learned process, which NASA
my gosh,
they try to keep this alive, but it's really not uniformly of high quality throughout the different subdomains. But it's a really interesting story for another day. But we should get together and talk about this at some point.
I'm really interested in lessons learned because in general, in my experience, 90% of those systems fail and lessons are not learned. And I think
they're learned and forgotten. They're learned for a while, and then people retire out. Anyway, that's a whole other
learned
topic.
by individuals. But the way that also connects exactly with all of these other topics we're talking about is culture. It's social culture. And that makes people communicate effectively and receive effectively and persist in problems.
And institutional culture, which is another.
That's right.
Okay, let's go back to, if you don't mind, unless there's another major topic in this branch, let's go back to the mission. So you've got these pair of imagers, which are also star cameras. Is that true?
No, star cameras are separate.
Oh, okay. Because they say they're used for navigation in the stuff I was reading.
So we'll be using them a bit during approach and orbital dynamic. We have to calculate what orbits are going to be stable because we don't know what the gravity field is. And so we'll be using the cameras a lot to understand what's passing underneath us on the asteroid.
Okay, so but the cameras have other purposes as well. Like they're visible near IR with a bunch of filters. And they can do stereo, although there's not much spacing between the cameras. So you'd probably do stereo just as well with sequential imaging. But could you say, let's go to the imager first. Can you say what are the questions that you hope to answer with the imager, and maybe what other surprises might it have in store?
Yeah, the number one thing is, what is the morphology of a body that we think has a partially metal surface? Is it going to even look like other asteroids? Can you make a regolith out of metal or only out of silicates? Metal is not broken apart by solar wind the way silicate grains are. So lots of questions about morphology. That's one of our primary science questions, is what is the morphology of this body? So that's a really big one.
Morphology means the structure and the materials, or what does it mean?
If I'm just talking about structure right now, but then of course the question is materials. What are we looking at? Part of that will be the gamma ray neutron spectrometer, but the footprint on that instrument tends to be large. And if we want to look at the resolution of the camera images, we need to use filters. So we designed this filter wheels for that go at specific wavelengths that help us recognize particular minerals that we expect to have on the surface of Psyche. So gamma ray neutron spectrometer does the elemental composition.
Quick question on that. What you keep saying, gamma ray neutron, is that like one physical process, one instrument, or is it two different spectrometers? One that
I'm slurring my words. It's gamma ray and neutron spectrometer, but it's really four. There's a gamma ray spectrometer, and there are 3 neutron spectrometers that measure neutrons at different energies. I can certainly talk to you about that. But
what do they tell you? The elemental composition?
They tell you the elemental composition. Yeah, so we're used to things like near IR spectrometers and things that Phil Christensen flies on all these planetary missions. And they are sensitive to the absorption features of crystals. And so they tell you minerals. But the gamma ray neutron spectrometers are sensitive to the gamma rays given off by individual atoms that have been hit by cosmic rays. So they tell you the identity of atoms, not mineral crystals. So with the imager, we'll get some mineralogy information as well as the morphology of the surface. And indeed we'll do topography with them.
So is there like is it sending gamma rays to the surface, or is it just looking for them?
It's just looking for them. It turns out with these airless bodies, they get hit by so many intergalactic cosmic rays that you can measure the composition of their whole surface just from the gamma rays that those struck atoms emit as they de-energize after getting struck by a cosmic ray.
Oh, that's fascinating.
Isn't that amazing?
There's been some lunar versions of that, Clementine. things like
Exactly. So we expect to see radically different data than was seen by gamma ray spectrometers for Mercury or for the moon. And also in the neutron counts, apparently metals give a very different neutron signature than do silicates.
And is the neutron, it's the same way, right? They emit neutrons because they're struck by high energy cosmic rays. Okay,
Exactly.
cool. So let's get to the metals, or no, not that particularly, but presumably there are these, you said you had your science flow down matrix. That might be an interesting thing to put on screen, but in any case, so you want to know the morphology and the composition and the gravity field and the magnetic field, but aren't there like higher level questions that we're going for here? Like, how did Psyche form? What does it tell us about the early solar system or the formation of the asteroids? Because the asteroids, correct me if I'm wrong, as I understand it, the asteroid belt is not like a planetary ring that's inside the Roche limit. Obviously, it's not. It's a ring of planetesimals and whatever else that came about through some other manner. It either never coalesced into a planet or it was broken up or something, right? Where do we stand on this? And what is this
Yeah.
going to tell us about these open questions?
Yeah, the dynamicists say that probably very little of the asteroid belt formed in situ. Probably almost all of it was implanted into that region, which is available for stable orbits for small bodies because of the big gravity field of Jupiter, preventing another planet from forming there, but little bodies can orbit. So implanted from energetic impacts in the inner solar system that throws material outward, and also things thrown inward from the outer solar system, including the hypothesized movements of the giant planets in the early solar system. Maybe even, for example, the question is if there's a very sharp inner boundary to the Kuiper belt outside of the last planet, and so we think that maybe Neptune and Uranus both moved and basically sheared off all those small bodies and threw them into the inner solar system. Some of them ended up in the asteroid belt. So we think that the asteroid belt is made up of bodies that formed outside of Jupiter and bodies that formed inside of Jupiter. And
inside the orbit and outside the orbit.
Inside the orbit of Jupiter. Yeah, sorry, not inside the body of Jupiter. Good point. And so they're mostly made of rocky materials of a variety of different kinds. And then a few that seem to also have large regions of metals. Primitive asteroids and the meteorites that come from them all have metal on a very fine scale, but only a few of these asteroids seem to have a large amount of metal.
Cool. Okay, so I'm going to ask a question for a friend who can't be here in a minute, but first, this metal body, which they always render with like shiny metallic colors, as we saw, it's a mystery in some sense, right? Like I know that the standard talk is, well, it's probably the core of a planet or an almost planet, and somehow the mantle or the outer stuff is gone. And we're just like, one of the things, correct me if I'm wrong, is that this might allow us to have a direct look at a metallic core of a planet like the one on the Earth, which we can't directly observe. Is there more to it than that, or is that just the story?
That's what we would call our fiducial hypothesis. It's the simplest way that we know to make a lot of metal in one place is through core formation. And the original cores were formed in planetesimals that melted because of the heat of short-lived radioisotopes in the early solar system. So we know that some of them had cores, and we can tell that from meteorites. But do we know that to be the situation? Absolutely, we do not. So the prime evidence for Psyche having a lot of metal, one is its density, which seems to be about 4,100 kilograms per cubic meter, which puts it much more than any rocky asteroid or meteorite, which tend to be very porous and well down below 3,000 kilograms per cubic meter, but not as much as solid iron nickel, which is more like 7,000. So it's like half and half or something like that. Is it half and half like a big chunk of metal core with silicates around it, or is it all still mixed up and never melted? That's also possible. And so I've been talking about this enigmatic object now for 13 years, giving talks all over the world. And I always ask scientists, what else could it be? And besides a planetesimal core, and there's a whole spectrum of possible answers.
Do they ever say, did you ask Avi Loeb? And did they ever say it could be a techno object?
I never asked Avi, but I did have someone tell me that it cannot be the Death Star because it's too small, and it cannot be the Death Star prototype because it's too big. So can just cross this off.
Okay, that's good to know.
Yeah, good to know.
Okay, now the question for my friend. Is there any talk of utilization of these metal-rich asteroid or something like dragging it to Earth or dragging it to Earth orbit and mining it or smelting it or doing or like I know this is far future stuff, but is this a thing? And does the mission have anything to say about addressing that issue? Not
Oh my gosh,
that they can learn about.
so much to say. But the first thing I have to say is my official government sanctioned disclaimer. NASA does not mine space resources. This is a pure science mission looking only at science questions. Now for the part that I can answer as my separate human self. We've had hundreds and hundreds of headlines all over the world about how Psyche is going to make everyone on Earth a billionaire. And it cracks me up how this is just the biggest headline. Forbes has run this headline, and I talked to the writers at Forbes. I'm like, you guys, this is absolutely not true. And they're like, we write about space in Forbes. This is the most clicks we've ever had. It went up to do, but they've also debunked it in the article because it's
all about the clicks.
Yeah. So just to say, we all know on this call that we have absolutely no technology with which to bring an asteroid to Earth. We have no way to do that. And if we did, it would be a really bad day for Earth because we have no way to park it in orbit. And even if we could park it in orbit, it would crash the markets and then it would be worth zero. So that's not a way to go. But we will get the first images of if it is what we think it is of a metal surface. And that would give all these companies that want to mine space resources some data on which to plan their landers. And there are a handful of companies around the world that are really working on space resources. Planetary Resources, of course, was way ahead of the pack and a little early, I think. I do a little advisory work for Astroforge, and I think they have a really cool idea. So trying to figure out ways to bring back basically platinum group elements or things that would save the Earth from mining and be really valuable. Everybody talks about water in space, but there's no economic closure for bringing water to Earth. It would be for use in space, and we don't have any businesses that have business cases that close in space yet. So that's all pretty futuristic.
So are the neutron and gamma ray spectrometers going to be able to assay for precious metals? Probably
not. We can get some more trace elements like potassium. We can get hydrogen, but an iron nickel meteorite metal, of which we have so many samples on Earth, all of the atoms that like to live in metal dissolve into them. So the siderophile elements. So you get iridium and rhenium and cobalt and palladium and platinum and gold and silver all in minute quantities in this meteoritic metal. And so they'll all be there, but in very small amounts. Although I did actually calculate the value of just the iron in Psyche on the metals market of January 2017, it would have been worth $10 quintillion. Or in other words, it would have been worth nothing because it would
have supply and demand. Yeah.
Yep.
Yeah. Very cool. Okay. So let's see. We don't have questions in the chat. Does anyone want to just chime in? Well, I don't see any questions. Allison, would you? Does anyone want to chime in on audio and ask a question? Because I can keep going.
We answered every question.
Oh boy. Okay.
Oh,
Well,
but you keep going for a while because sometimes it's good to give people a reminder that they can ask questions.
Yeah.
Oh, Micah is very happy with your questions.
I want to ask everyone who's here a question, and you can put it in the chat if you're not chatting, but I'm really curious about people's involvement with asteroid and space mining and level of interest in it or connection or hopes. I'd love to hear your thoughts on that.
okay. Look, I have a kind
I'll
of
start with Creon.
I have a snarky story about that, which you'll find.
Excellent. Excellent.
So back in the early days of Planet Labs, where I've worked for the last 9 years, the Planetary Resources was also starting up at the same time, and this from a similar background. And Planetary Resources, after a while, I believe it was a couple years in, they said they had changed from trying to do an asteroid mining mission to do an asteroid characterization mission. And then they realized that after they'd been working on this technology for characterizing asteroids, they were like, we can use this for Earth observation. So we're going to pivot and we're going to become an Earth observation company. And so Planet Labs, which already was an Earth observation, we always give an April Fool's announcement about something, and I wanted us to announce that we were pivoting to become an asteroid mining company.
Oh, that's so funny. I like that snarky story. Yeah, that was rough watching Planetary Resources have to go down that pathway, but man, oh man, it's very ambitious to try to mine asteroids.
Yeah, we probably need something. We wanted to colonize Mars and mine the asteroids. Some people want to build solar power satellites. And the problem is all of those things are just, while they're obviously possible from a physics standpoint, they are not economically, they would cost so many trillions to actually do that it's hard to see how they would ever actually achieve economic closure. And we need to find some kind of intermediate business cases, as you alluded to.
Right.
If we're enthusiastic about space and just think space is the answer, even though we don't know what the question is, then we need to have some sort of intermediate economic goal that doesn't cost trillions of dollars. And so
That's right.
the only one I've ever heard, and I'm always interested in these space talks to hear if anyone knows of another one. The only other one that I've heard of that's not already been done for decades, like Earth observation, communication satellites, and
That's right. We got all that.
Yeah, O'Neill colonies are another example of
the opposite of an intermediate goal, but something we would all like.
Now, one that I heard of is prospecting for volatiles on the moon to use as propellant for geotransfer orbit and stuff like this, because it's allegedly, if you could get it set up on the moon, which is easier than mining the asteroids, if you could get propellant mining on the moon, it's much less delta V to send propellant from the moon to GTO than to send it up from the Earth. So maybe propellant from the moon could have an economic case, and it's an intermediate step. I don't know the details. Do you know of any other proposals for an intermediate step that we aren't already doing?
No, I don't. And I wish that I did, because then I would be doing it. But I will say there's a really interesting question about volatiles on the moon. Some of them are created by protons from the sun scavenging high electrons and becoming hydroxyls and so forth and hopping around. And some are very early volcanic degassing, but most, we think, of the volatiles on the moon are from impacts in the relatively recent past. And so that would be comets and asteroids. And comets and asteroids don't deliver pure water ice cubes. They deliver a mess of ices and a mess of toxic and soluble and insoluble organics. And this is a kind of a messy ice, things that would be filled with amino acids and long chain hydrocarbons and stuff that's constellated with mercury and arsenic. And we just don't have any water purification systems that would work for it. And people always say, well, just use the one from the International Space Station. Will not work.
Well, okay, but if you're going to use water as propellant, then it's the purity is such as it's required this for different purpose. Okay.
We have another question from Chris,
Yeah,
if you want
we
to
do.
unmute.
I'll go to him in a second. I wanted to just mention that one neat thing about Mars, right, is that it does have vast quantities of water ice and CO2 ice. And
Yep.
so if we can get there, it's not like mining stuff from the moon, which is ridiculous in the sense of the concentrations. On Mars, it's like you just scoop it up. Okay.
Yeah.
All right. So let's see.
Yeah.
We have a question from Christopher Johnson.
Yeah.
Do you want to
Hi there, everyone. Hi, Lindy.
Chris.
Hope everyone's doing great. So I work a little bit more in the planetary defense side of things, and we just had a space mission planning advisory meeting, the same page meeting on the sidelines of IAC. And I posted in the chat the 2025 asteroid threat scenario, a hypothetical but potential scenario. You can take a look at it. But my question is general and honestly like really basic because I'm not science minded particularly. How do science missions like Psyche, let's say, overlap or intersect or complement planetary defense capabilities, including like the asteroid threat redirect capabilities, which we want to have?
Yeah. The thing I always think is that you were conditioned by Hollywood to think that every asteroid is like every other asteroid. But every asteroid that we go to seems to be different in some very fundamental way. And so understanding the structural integrity and the surface characteristics of a new kind of asteroid is only going to help us if something like this is coming toward the Earth and we need to understand how to redirect it. But that is about all that comes to mind when people ask me that question. It's really, especially in the case of Psyche, so far away, so non-intersecting. What we're really doing is learning about a new kind of body. And so to the extent that can help us, that's a good thing.
Oh, sorry. Go ahead, Chris.
Yeah, that makes sense. Sometimes in the asteroid threat mitigation technologies, it's a different scenario if it's a rubble pile or if it's a rocky asteroid or if it's a metal asteroid. And for something like the size of Psyche or something honestly larger than like 60 meters, if it's metal, the technologies are a lot different, and we're looking
Totally.
at nuclear explosive devices as opposed to redirect, unless you have 100 years and you can use like lasers to move the trajectory of it.
That's a really interesting question too, is should you ever blow up the asteroid that's coming toward you? Because then you will just shower the Earth with small pieces. Which
That's not how the nuclear option is. The nuclear option is to detonate a nuke and not to fragment the asteroids per se, but to have it vaporize stuff, have it outgas, and propel it in a new direction.
Yes. And hope that you're really lucky.
Yeah, right.
And hopefully what would happen is you would see the orbit coming closer to the Earth, and you would do it after it had passed the Earth on a previous orbit, because you don't want any extra junk in Earth's orbit either for Earth to sweep up. So that's a very complicated problem.
Ideally, you'd test it on an asteroid that had no chance of coming near the Earth just to see if it even works. Okay. One more question about the mission. What is the situation with your propellant budgets, your power budgets, your financial budgets? Is there the possibility of an extended mission? And if so, what might be something you'd like to do?
Yeah, we should be okay for an extended mission. Our primary propellant is xenon, and we're flying well over 1,000 kilograms of xenon.
That's not
brief. No, but you know what? We did a really brilliant thing, and we bought it early because guess where xenon is mostly made?
Ukraine.
Wuhan, China, and the Ukraine.
Yeah.
It was like, oh my God. Yeah, couldn't believe it. So we bought it before all that happened. And then we had a lot of other missions begging us to sell them xenon. So we flew over 1,000 kilograms, which for a short period of time was the largest amount ever flown. So we're fine on that. And we should have enough nitrogen for our coal gas thrusters. And the money, we wouldn't have enough money, but it would have to be funded separately. Power budget is fine out there at Psyche. Our biggest consumable problem right now is actually the reversal cycles on our solar array, the joint, the SATAs that connect the solar arrays to the body of the spacecraft. So we have to work on that.
But you could mitigate. If you lost control of the solar panels, you can still point them towards the sun. It's just compromises other activities, doesn't it?
It compromises all the other activities. So it's very complicated with this solar electric.
Do you carry magnet torquers in the sense that if this does have an interesting magnetic field, you can start to use it the same way we use the Earth's magnetic field for? Oh no, okay.
No, so the extended mission that we're likely to propose, should we ever have the chance, because of course you can't make anything official till you're declared success, would be to just orbit down closer and closer to the surface and get better and better images. That would be our plan for extended mission. There's not going to be handy other asteroids nearby, even though it looks so crowded out there.
Interesting. Okay, that's cool.
We have another question from Micah, if you want to unmute.
Micah?
Mike is broken, so I'm going to ask it for him. How big is the vessel heading to Psyche, and do you have any images of it?
Yeah, let me show you a couple pictures. The chassis of the spacecraft is about 3.2 meters on a side. Here it is, having just arrived at Jet Propulsion Laboratory from Maxar. So there's the bus of the spacecraft. Can you see my little arrow?
Yes.
Maybe you can't.
Yep.
Yes. The silver guy here is the high gain antenna. These are 2-meter booms for the magnetometers and the gamma ray and neutron spectrometers with an optimized structure. This is one of Maxar's patents, is that structure. So there it is coming in. Here I am sitting under it with our assembly test and launch ops manager, Brian Bone, who's pointing with his flashlight at the comms panel that had just been installed. These are our thruster arms. They have an elbow and a shoulder. We have 4 thrusters, each with the red removed before flight cap on them. This is what they look like when it turns out ionized xenon is blue, and that is what's happening in space right as we speak at this moment. A little part of our team, some student art. Here's one of the solar arrays. We're practicing extending it. They're really shaped like a plus, but this particular piece of gravity offloading equipment that let us extend the solar panel under Earth gravity doesn't do the cross pieces. In space, when both of these solar arrays are out, it's almost 25 meters across, about the size of a singles tennis court.
Are articulated panels with 1 degree of freedom, or what's the story here?
Yeah, 1. That's right. And then that's our shipping container, and coming off the C-17 at Kennedy.
Where was it built?
It was built at Maxar in the Bay Area and Jet Propulsion Laboratories, where all the integration happened, and then the final assembly test and launch ops at Kennedy. There we are right before encapsulation with the solar arrays all folded up on the spacecraft.
What's the wet mass?
Don't remember. Sorry. Yeah, number that's left.
The dry mass plus 1,000 kilos of xenon.
Exactly. That's what the wet mass is. Yeah. Yeah. So they're pad 39A and those same. And in case, I'm sure everybody on this call has tried to bring into their minds the scale of a rocket, but that the fairing up at the top is 4 stories tall, this 4-story building. And that's, of course, where the spacecraft is. And then I have a little launch video I can show you if you want.
Sure.
Yes, please go.
That's a good.
Go.
That's a good
20
knowledge.
seconds of launch. 5, 4, 3, 2, 1. Engine ignition. And lift off. Lift off of Planetary Psyche on a mission to a metal asteroid in deep space to study the building blocks of our planet's inner space.
Did you get to see the landing?
Yeah.
Great shot there on the side listeners coming off the right. There it comes. Perfect landings for them both. I keep a look up for each thing. There it is. The Psyche spacecraft going off into deep space. We have a signal that says, hey, I'm here. I'm out in space.
Oh, there's the cross-shaped panels. Cool. Yeah.
We have one more question as well from Ekaterina, if we have time, but this was very cool.
For sure.
Please go for it.
Yeah. Hi, thank you so much, Lindy, for really amazing talk. My question is, especially when you all started discussing mining and space resources, my question is, have you watched For All Mankind? And if yes, what we should do basically to achieve the same in our reality. Because in this TV series, the humanity was quite successful, right? Of course, they had their problems as usual. But I think it's something that a lot of the space enthusiasts would love to see in real life. So what do you think? What should we do?
Yes. What should we do? I've watched a part of that series, and I really think that everything humans do comes down to how humans interact. And I think that really working hard on how big teams work together and trying to create a more equitable world, becoming interplanetary is an unprecedented chance for wealth and equity greater than any in human history to date. And so I think that including people, including nations, including groups in the effort is going to be one of the keys to making it work. That is having fewer enemies. That's my top line answer. What do you think? What's your answer?
Thank you so much. I think I agree with you because right now I think we're thinking more about to be first or to do something.
Yes.
We consider sometimes space maybe as a part of this kind of national power advantages and stuff like that. And we are not thinking that, hey, we want to make the future to be our reality. This is not the strategy that governments use around the world.
I agree with you. If we could just make it not a proxy for war, that would be such an amazing step. So that's what you all are doing. I'm counting on you.
Look, one follow-up on that, which I'll just say is that it's too bad that the Russians were excluded and that we screwed it up with the Chinese and the space station. But the thing is that even if we have a unilateral or multipolar competition for space activities, humans or science missions, it's a good thing. It's a soft power competition. It's an alternative to war. It's a way of signaling the power of your civilization without just building weapons.
Yeah, it's true. It has a peacekeeping activity. It's like nuclear weapons can have a peacekeeping activity as well. But I would yearn for a greater good eventually.
Yeah, but what I'm trying to say is it's arguable that competition between nations and groups of nations in peaceful space activities is for the greater good and may even be greater good than if you tried to coordinate everybody, because that's just so hard.
We don't have to all do it together in the same project, but I think we have to do it together in the sense of humanity. Yeah.
Now, let me ask you something. Allison, do we have to quit?
We're at time. I don't know about Lindy. You probably have a hard stop. I'm not sure.
I have 2 or 3 minutes.
All right.
Okay. Ask your final
One more
question.
question. There have been other missions to asteroids, right? And comets and minor bodies. How did they inform the Psyche mission?
The one that informs us the most is Dawn, because we're using some of their same operations that they developed.
Dawn, what are the basics of Dawn?
Oh, it was a different kind of solar electric propulsion, also going to Vesta, which is bigger than Psyche. But some of these bodies visited have been so tiny that they have a negligible gravity field. And so people just orbit in a square around them because why not? And what we're trying to do is actually get into a gravitational orbit of a very unevenly shaped body. So that's been really helpful to see what Dawn went through at Vesta.
Fantastic. Lindy, it's been great to catch up with you. And I look forward to discussing lessons learned in the future at some point.
I appreciate it. Me too. And keep up your good work. And
that was extremely informative. Thank you so much.
Good. Look forward to doing things with you all in the future. So take care. Thank you very much.
Thanks a lot. Thanks for joining. Thanks for your great questions, everyone. Bye-bye.